Next part of this section, we talk about compound interest. And in order to talk about compound interest, we'll start with the formula for simple interest, in that the interest is equal to the principal balance, that's your starting balance, or the amount you deposited, times the rate, which is your interest rate, we represent that as a decimal, times time in years. And what we say is, when we compound interest, that means that we're paying interest on the principal balance and the interest already earned. This is what happens with your savings accounts, with your credit cards, pretty much with everything is calculated with compound interest. So what we'll do is we'll say, okay, well, let's let our time be equal to a year. So at the end of a year, the amount that's in our account is the original principal plus the principal we had times the interest rate times 1, which is the number of years. We can factor P out of this, and we get P times 1 plus R. Well, this will continue each year. So our first year we had P times 1 plus R. Then our second year we had P times 1 plus R, which was our new balance, and we actually multiply that by R. So what we're able to do is factor some things out, and we end up with P times 1 plus R times 1 plus R. We factor or we simplify that rather, and we end up with P times 1 plus R squared. So in the second year, this is how we know how much is left in our account. In the third year, we have what we had in the second year, P times 1 plus R quantity squared, plus P times 1 plus R quantity squared times R again, which gives us P times 1 plus R squared times 1 plus R, right? Because we have factored. So what that means when we simplify this further, now, do I expect you to be able to do this every time? Absolutely not. What I'm doing here is I'm showing you how we are going to derive the formula, because in the third year that we've had our account, we have our principal balance times 1 plus the interest rate, and this exponent is the number of years that we've got happening. So this will continue so that A, which is what we call the future value, is really this. Now, of course, you're looking at this formula saying, okay, well, what happened? Well, the thing is, in the last formula, we were making one payment every year, one payment of interest per year. We can actually make multiple interest payments per year. For example, we could pay semi-annually, in which case there would be 2 payments per year, and you divide that interest rate by the number of payments you make. Or you could pay quarterly, which would mean you're making 4 payments a year, or monthly would mean that you're making 12 payments a year, or you could pay daily. So we actually extend to this formula, and this is the one that you're actually going to be using. We take our principal balance, we multiply it by 1 plus the interest rate divided by the number of payments a year, and that's a big one. We raise that quantity to the power of the number of years times the number of payments per year. And that's going to tell us the future value of the account. So now we actually get to try one. Okay, we're going to take $25, we're going to deposit it into an account that pays 6% per year, compounded semi-annually. That means every 6 months or twice per year. We need to find the amount in the account after 10 years. We actually have all the information we need. The principal balance is $2,500. The rate is 0.06 because we always take our percent and write it as a decimal. The time is the number of years, that's 10. And then N is the number of payments every year, which is 2. So now if I'm going to find the amount, that's what I put into my calculator. That's what you should put into your calculator. We find the answer is $4,515.28. The question next is, well, how much interest did we earn? Well, we didn't take anything out. We also didn't put anything in. So the amount of interest we earned really is the total amount we have left minus the amount we invested. And we earned $2,015.28 in interest. Now, of course, these are word problems, so you're probably going to be writing sentences. So Leah evidently has some bills she has to pay in 8 years, and she has to pay the whole thing as $15,000. So she's going to deposit money into an account today that earns 4.8%, and it's compounded annually, which means one time a year. How much does she have to deposit so that she gets this $15,000 in 8 years? So for this one, we already know what A is. A is $15,000. We don't know what P is. That's what we're looking for. Our interest rate is 0.048. The time is 8 years, and N is 1 because it's compounded annually. So I can set this up. And actually, I don't even have to use that as a fraction because N is 1. So what am I going to do? Well, I'm going to take this, put that into my calculator first. When I do, I get this. 15,000 is equal to P times 1.455. Well, now that's really easy to solve because all I have to do is divide both sides by this 1.455. When I do that, I get $10,308.63. So Leah has to deposit this much money, getting 4.8% interest compounded once a year for 8 years in order to be able to withdraw $15,000. Well, let's suppose she only has $10,000. That extra $308.63 doesn't exist. What does her interest need to be so that she can make sure she's got $15,000? So again, we know that A is $15,000. The principal in this case is $10,000. We don't have an interest rate, but the time is still 8 years, and the number of interest compoundings is once a year. So let's get this equation set up. 15,000 is equal to 10,000 times 1 plus r, and normally we would put an r over something, but that thing is 1, so we can just leave it 1 plus r to the power of 8. Now this might seem a little bit challenging, but we're going to just reverse the order of operations, and we're going to divide by 10,000 on both sides first. When I do that, I get 1.5 is equal to 1 plus r to the power of 8. Now I need to undo this exponent, which means I need to raise everything to the 8th root. And you're like, Miss Busselmeyer, that does not exist in my calculator. You're right, it doesn't. So it's 1.5 to the power of 1/8 is what you'll actually put into your calculator. And when you do that, you will get 1.05, we'll say 20. So I should definitely write that a little bit better. 1.0520 is equal to 1 plus r. Well, now it's really easy. You subtract r from both, or 1 from both sides. I'm going to come up here, and you get 0.0520 is equal to r. That's not really a percent. We're looking for an interest rate, so we multiply it by 100. That should be pretty common knowledge. So our interest rate here is 5.2%, which means that if she only has $10,000 to deposit and she's getting it compounded annually one time a year, then she needs to find an account with 5.2% interest to keep it in for 8 years so that she can ensure she has $15,000. Now, the thing about compounding is that the more times you compound, the more money you get, the more interest you earn. However, there is actually a limit on the amount of interest that you're going to earn no matter how often your interest is compounded. So to illustrate what happens as we increase the number of compoundings, we're going to use some pretty simple values. We're going to start with $1, and we are going to invest it at 100% interest per year, compounded n times per year. So we don't know how many times it's compounded. So in decimal form, our interest is 1. And the interest rate is 1 over n because we don't know how many times a year it's compounded. And our p here is equal to 1. So we would write this, a is equal to 1 times 1 plus 1 over n times 1 to the n power, because we're talking at the end of 1 year. That's where they get this. Well, what they did was they took that equation and they put that into their y equals. So this was x and this was y1, and they looked at the table and they looked at some specific values, as in at the end of 1 year, or with 1 compounding a year, we have $2. With 2 compoundings a year, with 5, with 10. Well, what if we compound $1 million a year, or 1 million times in a year? Take a look at these last sets of numbers. They're getting really, really close to about the same number. So from 10,000 to 1 million compoundings in a year, we're not off by very much. This is what we call E. In mathematics, E is a real number. It's irrational, which means you're not going to be able to write it as a fraction. But it is a real number, and that's why we don't use it as a variable. Now, the other thing that you need to understand is that the way we define E, and this is a notation that you will probably see in the future, is that E really is the limit as that number of compoundings approaches infinity, right? As if we're getting infinite amounts of compounding of this expression. So as n, as this number of n gets larger and larger and larger and larger, we are going to approach a number that's closer and closer to this E. Okay, you see how this is 2.718? That's what we call E. You don't have to have this memorized. I'm just explaining so that you understand where it comes from. Here's what E looks like to 9 decimal places. What do I want you to know? 2.718. That's what I'd like you to know about E, that it is approximately 2.718. So as we approach infinitely many compoundings over the course of a year, we call this continuous compounding. And the way that the equation changes is this. Instead of having, like we had before, we had p times 1 plus 1 over n to the power of t times n. We took all of this and we changed it so that now really what we're looking at is the principal times this e value to the power of the interest rate times time. That will give us the value of the account when it is compounded continuously. So now we'll do a problem that deals with continuous compounding. Let's suppose we have $8,000 in an account that pays 5% interest compounded continuously for 6 years. How much do we have at the end of 6 years? Simple enough. My principal balance is $8,000. My rate is 0.05. My time is 6. So the amount in our account is equal to $8,000 times e to the power of 0.05 times 6. You will need to put this into your calculator. When you put this into your calculator, please make sure that you put parentheses around this product. Otherwise, it will multiply this whole thing by 6. So make sure you've got parentheses. So as I enter that into my calculator, the amount that I have is $10,798.87 at the end of 6 years when we compounded continuously. Now we're going to do some comparisons. That $2,500 deposited at 6% that we did in like the first problem, we had it compounding twice a year. We're going to compare these values with continuous compounding. So we know that the principal balance is $2,500. Our rate is always 0.06, and our time is 10. So the first question, what if the value is compounded quarterly? So in this case, n is 4. So A is equal to 2,500 times 1 plus 0.06 over 4 to the power of 10 times 4. And this value is $4,535.05. Please pay attention to this part. On my calculator, that decimal said 0.046. Because the third number was a 6, I rounded so that it was 0.05. A lot of you are still making this mistake. Let's take a look if the interest is compounded monthly. In that case, n is equal to 12. What changes in our equation? Well, we've still got A. We've still got 2,500. We've still got 1 plus 0.06. This time we divide that by 12, and we take that to the power of 10 times 12. So in this case, the value of the account is $4,548.49. So we notice the difference between compounding quarterly, compounding monthly, is a difference of what, $13 in a year. Let's take a look at compounding daily. Here we'll say 365. And the value of our account is $4,555.07. So again, we've increased, but this time not quite as much. So the daily compounding from the monthly compounding is a smaller change than month from quarterly. Now let's look at continuous compounding. So this one, remember, is a little bit different because the equation is A is equal to PE to the power of RT to the power of 0.06 times 10. In this case, the value of the account is really not a very significant change at all. It's actually less than a quarter difference. One thing I don't think I mentioned before, in order to find the button for E, you push second and the division sign. That's where E is located. Otherwise, you can push second and the button that says ln, and that will give you e to the x. Either way is perfectly fine. This last slide is dealing with a regression. You guys know how to do regressions. We've done regressions before, and I'm not going through the steps again. Here, we're looking at some trends of burning fossil fuels and the amount of atmospheric carbon dioxide in parts per million. So here are the years, and then this is the carbon dioxide in parts per million. What you need to do is you need to input this data into your L1 and L2. So you'll go to Stat, Edit, and get this information in. And you'll use the equation. You're going to run an exponential regression. In your calculator, it'll say EXP regression, REG. So you're going to run an exponential regression, and you're going to get an equation. And then you're going to use that equation to figure out the carbon dioxide levels in the year 2015. Okay, so we're looking for something right in here. Then what I'd like you to do is to take that equation you get and put it into your y equals. And I'd like you to find out when the level is going to be double the year 2000 level. So double this, and then give me the year that this is double. I will be looking for this information in your notes.